In this video, I'm going to be talking about taking partial derivatives. So this is going to be like some real, it's going to feel like calculus. And so I'm going to kind of start with a situation that I want to talk about. We're talking about a parallelogram. Looks all right.
You talked about this and then you said we're never going to talk about it because it's evil.
So the parallelograms, the actual area inside of it depends not only on the respective lengths of, I'm going to try to draw this again. Okay, that's as good as it's going to be. The respective lengths of, these two things, like I'm going to call this A and that B. But it also depends on its angle, right? Because if I keep these the same and I flatten the angle, I'm going to have less area. We know that intuitively. So I'm realizing that A and B might not be the letters to use. I'll use X and Y or something like that. Because my area is going to be, I'm proposing that it's X times Y times the sine of theta. And maybe I could, give you a little bit more drawing on that. I don't want to waste too much time on this video going into why the area of a parallelogram is what it is, but I don't want you to sit there not believing me this whole time. So this is, really what I'm doing is I'm taking this triangle here and I'm just sliding it over here. So this horizontal distance is the same as that horizontal distance. I don't think I really am going to need to justify that for you. This height is this height, same height. And that's x times the sine of theta, right? Because the sine of theta is this length divided by x, so I can multiply both sides by the x and say that this length is x times the sine of theta. So this is x sine of theta. Therefore, because we know the area of this rectangle, and I know it's the same because I just slid that triangle over, I've got area equals x sine theta times y, which I can just write x, y, sine of theta. But you might be interested in, what happens if I stretch out y a little bit? What if I take x and I make it longer? Or what if I change the angle? What's going to be the change in the area? That's a derivative question, right? The derivative is like what's going to happen to the output of the function when I tinker with the input. Now this function has 3 inputs, right? So as I tinker with each of them, it's going to be a different effect. Right? And so now I'm going to give you the definition of partial derivative, and I'm going to just give it to you for x and y. In general, you know what it's going to be. Okay, it's going to be the limit of a difference quotient, as you might expect. But now we know what a limit actually means, so that's good. The limit. Okay, this is going to be the partial derivative of a function with respect to x, and yeah, so that's the limit as delta x goes to 0 of f depends on both x and y, so I'm going to bump up x a little bit, minus f of x and y, rise over run. Okay, and this is the derivative of f with respect to x. That's going to be one of the notations we'll use for that. We'll also say the partial derivative of f with respect to x. Okay, it's like a curly D. I can't remember if that's nabla or if that's
what's the curly D mean?
Partial derivative.
Partial.
And then, I can say the same thing about y, and I'm just going to tinker with y a little bit, let y get bumped up a little bit, analyze the impact on the function. So f of x and y plus a little bit minus f of x and y divided by delta y. And we call this fy, or partial f, partial y. Okay. So for this thing, I'm sure you could imagine what I mean when I say dA d theta, or dA dy, or dA dx, right? I don't need to write down that definition for any given variable because it all of a sudden gets a lot more, depending on the number. If you don't know how many inputs and outputs you've got, it's kind of tough to say what you mean. What else was I going to say? Oh, okay. And so I'm going to show you how to take one, with a couple of pretty quick examples, and then I'm going to jump back over here to this situation. So, for example, I've got z equals cosine of x times y squared. This, I think I'm going to give you the advice that people will give you when you start to take a partial derivative. If you go to take the partial derivative of z with respect to x, every other variable is just a number. You pretend that it's just a constant, right? Because we're going to, basically, when we're taking the derivative with respect to x, we're going to hold y constant. We're not going to change anything about the function in terms of y. Okay, so y we can consider to be a constant. So the derivative of z with respect to x is going to be, this is like cosine of 10x. Okay, we know how to take the derivative of cosine of 10x. It's going to be negative 10 sine of 10x. So the derivative of cosine is negative sine. Leave the inside the same, and then multiply by the derivative of the inside. Well, the derivative of xy squared with respect to x is just y squared. Yes, you're already getting the hang of it.
How is this a partial derivative?
Because we're taking it with respect to x and holding y constant like you were saying.
Oh.
Yeah. Because we're only considering the impact that x is making, basically.
Okay.
And we will be investigating this for, a couple weeks. We can also take the derivative of z with respect to y. Just a second. I'm going to take the derivative with respect to y, and then I heard that there was, I don't know, some kind of chatter in there. So I'm going to say, okay, I'm going to take the derivative of the outside and leave the inside the same. And then the derivative of y squared, that's 2y. Okay? And then that x is there.
XY?
So yeah, it's going to be 2xy. And so honestly, whenever I see, I don't know why I've chosen this number, but whenever I see the other variable, and I'm unsure which direction to go, I just think 10.
So it'd be 21?
Yeah, and so basically 2xy, yeah. Okay, this is the type of thing where you need to just practice it on your own. There are product and quotient rule implications in these, and there are situations that aren't encapsulated in this example that are going to come up. But for the most part, that's really that's the advice that you need, and then you need to be set off on a bunch of practice, with the opportunity to check your work and make sure you're not going down the wrong road. Okay, now I want to go back to the parallelogram and say, all right, what do you think is going to happen to this particular parallelogram? I think it's pretty obvious what's going to happen when I increase x and y. The area is going to increase. What's going to happen when I increase theta? Like in the traditional pre-calc sense, I'm going to open it up counterclockwise.
Well, I mean, to a point it's going to increase, it's going to increase.
It's going to increase and then it's going to decrease. So I'm going to hopefully be able to show you that in terms of the partial derivative of area with respect to theta. So what I'm going to do is
Is this equation asymptotic when the theta is close to 180?
I think what we'll find is that as theta gets closer to pi or 180 degrees, that the area will go closer to 0. I think that really what's happening is that it becomes obtuse, so like this theta becomes that angle, and then after 180 it would just be like an upside down one or something. I don't know.
Oh, okay.
Also it'd be an inside out one, which is why the area formula would give you something negative, right? If you had positive length, but an angle over 180 degrees, sine's going to go negative. So it has to do with that, but it's, what's happening. You can envision it. So the partial derivative of area with respect to theta. Well, that's just going to be xy cosine theta, right? Just a quick reminder about cosine. It's the x coordinate, right? So we're over here. We're somewhere between 0 and pi over 2. So cosine, cosine, this is the rate of change of area. We would expect it to be positive as long as cosine is positive, which is over here. Beyond the 90 degrees, once it goes obtuse, the area is going to start to decrease. And we kind of know that. We can see that happening. It's going to kind of like fold in on itself. And then basically, yeah, it's going to start to, and it's going to go towards 0 there because of, as we approach 180, that's going to go to 0. Okay. I think that's about, and okay, wait, I could also say, partial derivative of a with respect to, one of the side lengths, like say x, is going to be, well, that'll be y sine theta. But you're thinking if we're trying to mess with x and we're going to keep theta the same, well, this is going to be a positive number. So if we increase x, we increase the area, which is something we already knew. Okay? And I think that's all I've got to say to you about, just the idea of partial derivatives and how to take a couple of easy ones. And then I'm going to let you practice on your own. Good luck.